In this video, we will discuss the concept of prime factorization. One of the most important theorems in mathematics is called the fundamental theorem of arithmetic, which is stated as follows. Every integer greater than 1 can be written uniquely as a prime number or as a product of prime numbers. For example, the number 45 is equal to 5 times 9. 5 is a prime number, but 9 is not. However, we can write 9 as 3 times 3, and 3 is a prime number. So, the number 45 is equal to 3 squared times 5. Similarly, the number 60 is equal to 10 times 6. Neither 10 nor 6 are prime. However, we can write 10 as 2 times 5, and 6 as 2 times 3. 2, 5, and 3 are all prime, so the number 60 has a unique prime factorization of 2 squared times 3 times 5. We can continue this process for any integer greater than 1. For example, the prime factorization of 72 is equal to 2 cubed times 3 squared, and the prime factorization of 32 is equal to 2 to the 5th power. While the process of breaking composite numbers down into their prime components may seem easy for small numbers, when large numbers are involved, this process becomes much more tedious. For example, consider the number 5,681. We can verify through division that the primes 2, 3, 5, 7, and 11 are not factors of 5,681. However, the next prime, 13, does divide 5,681 with a quotient of 437. Since the prime numbers 2, 3, 5, 7, and 11 are not factors of 5,681, we also know that they will not be factors of the quotient 437. If we proceed up our list of primes, we see that 17 does not divide 437, but 19 does with a quotient of 23. 13, 19, and 23 are all prime numbers, so our prime factorization is complete. Therefore, the prime factorization of 5,681 is 13 times 19 times 23. The general strategy for computing the prime factorization of an integer is to use division to test if the prime numbers less than the given integer evenly divide it. However, for very large numbers, there may be a great many primes less than that number. So, how do we know how many primes we should test, or where is the best place to start testing? To answer these questions, consider the following theorem. If an integer n greater than 1 is composite, then n has a prime factor that is less than or equal to the square root of that integer. To restate this theorem in a slightly different way, we can say that if an integer n greater than 1 has no prime factor less than or equal to the square root of n, then that integer n is prime. We won't prove this theorem, but we will do some examples to illustrate that the theorem holds. For the first example, let's determine if the number 359 is prime or composite. The square root of 359 is approximately 18.947, which is just less than 19. So, the only primes that we need to check are those primes that are less than 18, which are 2, 3, 5, 7, 11, 13, and 17. None of these primes divide 359, so, via our theorem, we know that 359 is prime. What about 1,237? The square root of 1,237 is approximately 35.17, so we only need to check the primes that are less than 35. None of the primes less than 35 divide 1,237, so this number is also prime. Finally, let's look at 1187. The square root of 1187 is approximately 34.39, so we only need to check the primes that are less than 34. Both 7 and 13 divide 1187, so 1187 is composite, and its prime factorization is 7 times 13 squared. To conclude this video, we will discuss the relationships between prime factorizations and greatest common divisors. Suppose we have an integer a whose prime factorization is given by 2 squared times 3 cubed times 13 to the 7th times 31 to the 12th, and another integer b whose prime factorization is given by 2 cubed times 5 times 13 to the 6th times 17 to the 5th. While we could multiply these factors out and use the Euclidean algorithm to compute the GCD, the prime factorization allows us to compute the GCD in a much faster way. To compute the GCD, we use the exponents on each prime factor that are shared between both a and b. For the integers a and b described above, note that both a and b share the prime factors 2 and 13. The GCD of a and b will include each of these prime factors along with the smallest exponent that appears between them. For the integer a, the exponent on 2 is 2, and for the integer b, the exponent on 2 is 3. The GCD will have the smaller of these two exponents, so the GCD will contain a 2 to the second power. The other shared factor is 13, and the smallest exponent between the two integers that appears is 6, so the GCD will contain a 13 to the 6th term. Since 2 and 13 are the only shared factors between a and b, we simply take the two terms along with their exponents and take their product to compute the GCD. So the GCD of a and b is 2 squared times 13 to the 6th. In cases where the prime factorization is not provided, we first need to find the prime factorization before we can use this GCD shortcut. For example, to compute the GCD of a equals 20 and b equals 12, we first need to compute the prime factorization of a, which is 2 squared times 5, and the prime factorization of b, which is 2 squared times 3. Next, we look for all of the common factors, which in this case is only 2, and we take the smallest exponent on 2 that appears, which is 2. So the GCD of 20 and 12 is 2 squared, which is 4. Using the same process for a equals 36 and b equals 52, we see that the GCD of a and b is again 2 squared, which is 4. Finally, for the integers a and b whose prime factorizations are shown, we find that the GCD of a and b is equal to 5 times 11 squared times 13 cubed times 21 to the 5th.